In August of 2025, NASA scientists watched our star do something it had never done in the entire history of this kind of observation. They detected a radio burst, an ordinary one, the kind logged and forgotten every single day. Except this one did not stop. The longest such event ever recorded had lasted about 5 days. This one lasted 19. 19 days of our star broadcasting, refusing to go quiet, nearly quadrupling a record that scientists thought defined the outer edge of what was possible. And to even capture the whole thing, it took a fleet of spacecraft scattered across the inner solar system, passing the signal between them like runners in a relay. So what was the sun actually doing, and why could nothing make it stop? If a record-breaking mystery from our own star is the kind of thing that pulls you in, take a second to like this video and subscribe to the Sky Lab, because this is the kind of story we follow all the way down. Drop a comment and tell me where you're watching from, and whether a 19-day signal from the sun unsettles you or fascinates you. Now, let us get into it. Part 1. The burst that refused to end. In August of 2025, a team of NASA scientists looked at a signal coming off the sun and felt absolutely nothing. No alarm, no excitement, not even mild curiosity. What they were looking at was a solar radio burst, and solar radio bursts are about as ordinary as space weather gets. The sun produces them constantly. They're logged, catalogued, and filed away as part of the daily background hum of monitoring our star. So when this particular burst appeared in the data, the only reasonable reaction was the one the scientists had. They noted it, and they moved on. And that is the part of this story I want you to hold on to, because it is the part that makes everything that follows so strange. This event did not announce itself. It did not arrive with a flash or a warning or a single dramatic moment. It began as the most forgettable thing in the sky. The reason we're talking about it today, the reason it ended up in a peer-reviewed journal, and the reason it is the subject of this video is not how it started. It is that it would not stop. A normal solar radio burst lasts minutes. Some of them last a few hours. The rarer, longer ones, the ones that actually get a second look from the people who study them, can stretch out across a day or two. And the longest one anyone had ever recorded, the all-time champion, the previous record holder in this very specific corner of solar science, lasted about 5 days. 5 days was the ceiling. 5 days was the number that defined the outer edge of what this kind of event was understood to be capable of. This one lasted 19. 19 days. I want to let that sit for a second, because the human brain has a habit of hearing a number like that, and just nodding along, and I do not want you to nod along. I want you to actually feel the size of it. The old record was 5 days. This event did not beat that record by a little. It did not nudge past it the way records usually get broken, by a hair, by an afternoon, by a margin so thin you need a referee to confirm it. This event took the record and nearly quadrupled it. It ran for almost 4 times longer than anything science had ever seen before in its category. And it did that quietly, without ever once doing anything that looked, in the moment, dramatic. Think about how records usually fall. A sprinter shaves 0.04 of a second off a world record and the whole stadium loses its mind. A mountain of data and training and marginal gains, all of it spent to win by an amount of time smaller than a blink. That is what breaking a record normally looks like. It looks like an inch. It almost never looks like a mile. And when a record does fall by a mile, when something beats the previous best not by 4% but by 400%, that is usually a sign that one of two things has happened. Either the thing you were measuring just did something genuinely unprecedented, or the assumptions behind your old record were quietly wrong all along. Hold on to both of those possibilities, because by the end of this video, we're going to have to decide which one is true. And the honest answer might be both. Let me give you a way to fill the gap, because numbers on their own can slide right past you. The old record was 5 days. Picture 5 days as the height of a single-story house, a roof you could reach with a ladder. That was the ceiling. That was as high as anyone had ever measured this kind of event reaching. Now the new event comes along, and instead of adding another few feet to that roof, it stands up a building nearly 4 stories tall in the same spot. Same kind of structure, same category, same physics, and yet it towers over everything that came before it. If you had spent a career studying these bursts, if 5 days had been the number you quoted in every lecture as the extreme upper limit, and then 19 days landed in your data, your first reaction would not be excitement. Your first reaction would be suspicion. You would assume you had made a mistake. You would check the instruments, check the calibration, check whether you were accidentally looking at two separate events and mistaking them for one. That suspicion, that careful, almost reluctant double-checking, is exactly the process that turns a startling number into a trustworthy one. And the fact that the 19-day figure survived that process, survived the scrutiny and the peer review and made it into a journal intact, is itself part of why we can take it seriously. The event ran roughly from the 21st of August to the 9th of September, 2025. 19 days bracketed by those two dates, and for most of that window almost nobody knew anything unusual was happening, because a burst this long does something that no ordinary burst ever forces scientists to deal with. It outlasts the view. Here is what I mean. The sun rotates. From where we stand on Earth, it takes the sun roughly 27 days to turn once on its axis. We do not feel that, we do not see it, but it is constantly happening, and it has a consequence that matters enormously for this story. Anything sitting on the surface of the sun, or anchored in the sun's atmosphere, gets carried along by that rotation. It swings into view on one edge of the sun, travels across the face of the disk over a couple of weeks, and then disappears around the other edge. A feature on the sun is not a fixed thing you can stare at indefinitely. It is a thing on a slow turntable, and the turntable never stops. Now, for a normal radio burst, this does not matter even slightly. A burst that lasts 2 hours is born, lives, and dies long before the sun's rotation moves it any meaningful distance. The turntable is so slow, relative to the event, that it might as well be standing still. But a burst that lasts 19 days is a completely different animal. Over 19 days, the sun's rotation carries its source a very large fraction of the way around the visible disk. The thing producing this signal was not sitting still. It was on a journey. It was being slowly, steadily transported across the sun's face and toward the edge and then around it. The entire time it was screaming. And that is the first genuinely difficult problem this event created, and it is a problem worth understanding, because the solution to it is half of why this story is remarkable. If the source of a signal is moving, and if it is going to spend 19 days being carried around a rotating star, then no single observatory, no single spacecraft, no single instrument anywhere can watch the whole thing. It is physically impossible. By the time the event is halfway through its life, the source has been carried to a part of the sun that the original observer simply cannot see anymore. You would be trying to photograph a marathon runner through a window that only shows you one block of the route. So the scientists who eventually pieced this event together were not working from one clean, continuous recording. They could not be. They were working from fragments. A few days of observation from one spacecraft, then the source rotates out of that spacecraft's view, then a few days from another spacecraft positioned somewhere else entirely, then a handoff to a third and a fourth. The full 19-day record of this burst does not exist as a single file from a single machine. It exists because human beings took overlapping pieces, captured by spacecraft scattered across the inner solar system, and stitched them into one continuous story. We are going to come back to exactly how they did that, and which spacecraft were involved, because it is one of the most quietly impressive pieces of detective work in recent space science. But for now, just sit with the shape of the problem. The sun produced a signal so long-lived that watching it required a relay race across the solar system. And there is a quiet lesson hiding in how this began, one worth naming before we go further. The most important events do not always arrive looking important. We have a picture in our heads of discovery as a sudden flash, an alarm, a moment everyone recognizes at once. But a great deal of real science does not work that way at all. A great deal of it begins with something that looks utterly routine, gets logged without a second thought, and only reveals what it is through patience, through the simple fact of continuing to watch. This burst is a near-perfect example. Nobody felt a thing when it started. Its entire significance is a thing that accumulated day after day, while it refused to do the one thing everything in its category had always done, which was end. So if you take nothing else from the opening of this story, take this. Pay attention to the things that will not stop. Sometimes the most ordinary-looking signal in the sky is just an extraordinary one that has not finished revealing itself yet. This event was, in the technical language of the people who study it, a Type 4 solar radio burst. That name is going to come up again and again, so let us not be afraid of it. It is just a label. Solar radio bursts come in a few different flavors, and scientists, being scientists, gave them numbers instead of names. Type 2, Type 3, Type 4. The numbers refer to how the burst behaves, what it looks like in the data, and crucially, what kind of physical process is generating it. And the Type 4 category, the one this record breaker belongs to, is special in a way that matters for everything else in this video. A Type 4 burst is not produced by a single explosive moment. It is produced by something trapped. It is produced by a population of fast-moving particles that have been caught, held, contained inside the sun's magnetic field, and are radiating energy for as long as they stay caught. And that word trapped is the hinge this entire story turns on. Because if a Type 4 burst is the signature of trapped particles radiating, then a Type 4 burst that lasts 19 days is the signature of particles that stayed trapped for 19 days. Something on the sun built a cage, and that cage held against everything we understood about how long such a cage could possibly hold for almost 3 weeks. I want to dwell on that word, trapped, for another moment, because it is doing more work than it looks like it is doing. When we say particles are trapped, we are not describing something passive, like a stone sitting at the bottom of a well. We are describing a tension, an active standoff. A population of fast-moving energetic electrons inside a magnetic structure on the sun is not at rest. Those electrons are charging back and forth along the magnetic field lines at tremendous speed, and every single one of them would, if it could, fly straight out and away. The only reason they do not is that the magnetic field keeps bending their paths back. Trapped, in this context, means a balance is being held. Energy that wants to leave is being continuously, forcibly kept in place. And a balance held for 19 days is a very different and far more demanding thing than a balance held for an afternoon. There is one more feature of this event that I have to put on the table now, even though we will spend a whole part of this video unpacking it later, because without it you cannot understand why the science here was so hard. The previous record holder, that 5-day burst, was difficult enough to study, but a 5-day event, in the worst case, mostly stays within reach of a determined observer. 19 days does not. 19 days is long enough that the sun's rotation becomes an active adversary to anyone trying to watch. It is long enough that the question stops being only what is the sun doing, and becomes also how could anyone possibly see all of it. Those two questions, the solar one and the human one, are braided together through this entire story, and you cannot fully pull them apart. The sun produced something that, by its sheer duration, was almost designed to be impossible to fully witness, and the fact that we witnessed it anyway is not a small footnote. It is half the reason this event made it into a journal at all, so that is the mystery we are walking into. Not a flash, not an explosion, not a single violent event you could point to, something much stranger and much quieter. A signal that should have lasted hours and lasted 19 days. A record beaten not by an inch but by a mile. A source carried around a rotating star, screaming the entire way, while a fleet of spacecraft passed it between them like runners passing a baton. And underneath all of it, the real question, the one we're going to spend the rest of this video answering. What kind of structure on the sun can hold that much energy, that still, for that long? And how did we finally figure out where it was hiding? The answer is going to take us inside the physics of our star, out across the inner solar system, and straight into the difference between a thing that is genuinely mysterious and a thing that is merely wonderfully rare. Part 2. What a Type 4 burst actually is. To understand why this event broke scientists, you have to understand what a solar radio burst even is, and I promise you it is not as complicated as it sounds. So let us build it up slowly, from the bottom, because the physics here is genuinely beautiful once you can see it. Start with the sun itself. The sun is not a solid object. It is not a ball of burning coal or a campfire scaled up to the size of a star. The sun is a ball of plasma. Plasma is what you get when a gas becomes so hot that the atoms inside it start coming apart, when the electrons get torn away from the nuclei they normally orbit, and you're left with a churning sea of charged particles. Negatively charged electrons, positively charged ions, all of it moving, all of it electrically alive, all of it responding to magnetic fields in a way that ordinary gas never does. The sun is a star-sized cloud of this stuff, And that single fact, that the sun is made of charged particles instead of neutral ones, is the root of nearly everything dramatic our star ever does. Because charged particles and magnetic fields are locked in a relationship, they cannot ignore each other. A magnetic field tells charged particles how to move, and moving charged particles in turn generate and shape magnetic fields. On the sun, this relationship runs the entire show. The sun generates magnetic fields far down in its interior through the churning motion of all that plasma, and those magnetic fields rise up, punch through the surface, and arc out into the sun's atmosphere in enormous loops and arches and structures. Some of those structures are small, some of them are larger than the Earth many times over, and the plasma, the charged particles, has no choice but to follow them. The particles thread along the magnetic field lines like beads on a wire. Now, a radio wave is just light. It is the same fundamental thing as the light coming off your screen right now, the same thing as the warmth of sunlight on your skin, the same thing as an X-ray. All of it is electromagnetic radiation. The only difference between a radio wave and visible light and an X-ray is the wavelength, how stretched out or how compressed the wave is. Radio waves are the long, stretched out, low-energy end of that spectrum. And here is the key fact. When charged particles, especially electrons, get accelerated, when they get pushed and jostled and forced to change their motion, they give off electromagnetic radiation. They glow, and depending on exactly how they are being accelerated and what environment they are in, a lot of that glow comes out specifically as radio waves. So put it together, the sun is full of charged particles. The sun is full of magnetic fields shaping how those particles move, and whenever a population of those particles gets energized and accelerated in the right way, they broadcast. They send out radio waves. A radio telescope here at Earth, or a radio antenna on a spacecraft can pick up that broadcast. That is a solar radio burst. It is quite literally the sun transmitting, and us listening. Different things happen on the sun, and they make different kinds of transmissions, which is why scientists needed those category numbers. A Type 2 burst, for instance, is associated with a shock wave travelling out through the sun's atmosphere, a kind of solar sonic boom ploughing outward and energizing particles as it goes. A Type 3 burst is the signature of a stream of electrons racing outward along an open magnetic field line, away from the sun, at a serious fraction of the speed of a light. Each type has a characteristic fingerprint in the data, a particular way it drifts and shifts across radio frequencies over time. And a trained scientist can look at that fingerprint and tell you what kind of process is behind it. And then there is Type 4. Type 4 is the one we care about, and it is genuinely different from the others in a way that is going to matter for the rest of this video. A Type 2 burst and a Type 3 burst are, in a sense, events about motion. Something is travelling. A shock front is ploughing outward. A beam of electrons is streaming away. They are bursts about things going somewhere. A Type 4 burst is not about something going somewhere. A Type 4 burst is about something staying. A Type 4 burst is produced by a reservoir of energetic electrons that have become trapped inside a closed magnetic structure in the sun's atmosphere. Closed is the operative word. A closed magnetic structure is one where the field lines loop back on themselves, where they leave the sun and then return to it, forming arches and domes and cages rather than open highways pointing out into space. Electrons caught inside a closed structure like that cannot simply escape. They are stuck. They run up and down the magnetic field lines back and forth, bouncing, confined. And as they bounce around in there, energized and accelerated, they radiate. They broadcast radio waves, and as long as they stay trapped, and as long as they stay energized, the broadcast continues. That is a Type 4 burst. It is the radio glow of a captured population of electrons, radiating from inside their cage. And I want to draw out one more contrast between Type 4 and the other kinds of bursts, because it makes the strangeness of a 19-day event land properly. A Type 3 burst, the streaming electron kind, is over almost as soon as it begins, because the electrons producing it are racing away from the sun at a serious fraction of the speed of light. They are gone in moments. A Type 3 burst is a sprint. It is intense and it is brief, and brevity is built into its nature, because the thing producing it is leaving. A Type 4 burst is the opposite temperament entirely. Nothing is leaving. The whole point of it is confinement, and so a Type 4 burst can, in principle, last as long as the confinement lasts. Its duration is not capped by particles flying away. Its duration is capped only by how long the trap can be maintained. That is why, of all the burst types, Type 4 is the one where a truly extreme duration is even conceivable. You could not have a 19-day Type 3 burst. The physics forbids it. The electrons would be long gone. But a 19-day Type 4 burst is not forbidden by the physics. It is only forbidden by how hard it is to keep a trap loaded that long. And that subtle distinction between a thing that is impossible and a thing that is merely extraordinarily difficult is the entire space in which this record-breaking event lives. So now think about what the duration of a Type 4 burst is actually telling you. The length of the burst is not a measure of how big an explosion was. It is a measure of how long the trap held. A Type 4 burst that lasts 2 hours is telling you that some magnetic structure on the Sun caught a batch of electrons and held them, radiating for about 2 hours before the structure changed, or the electrons drained away or lost their energy. A Type 4 burst that lasts 5 days, the old record, is telling you about a structure that managed to keep its captured electrons radiating for 5 days. That was already considered remarkable. That 5-day event was the outer limit, the example people pointed to when they wanted to describe how persistent one of these things could possibly be. And this brings us straight back to the central mystery, the thread running through this entire video. This new burst lasted 19 days, which means a magnetic structure on the Sun caught a population of energetic electrons and kept them trapped and radiating for 19 days, almost 3 weeks. The cage did not fail, the electrons did not drain, the broadcast did not stop. For 19 straight days, something on the Sun held onto its captured energy and would not let go. Now, you might reasonably ask, why is that so hard? Why can't a magnetic cage just hold particles indefinitely? And the answer is that trapped particles are not patient. A population of energetic electrons confined in a magnetic structure is constantly trying to escape and constantly losing energy. They leak out at the edges, they collide with other particles and slow down. The radiating itself costs them energy. The magnetic structure containing them is not a fixed steel box. It is a living, shifting thing made of plasma and field, constantly being pushed and reshaped by everything happening around it. A magnetic trap on the Sun is less like a prison cell, and more like a person trying to hold a beach ball underwater. It can be done. But it takes constant effort, and the moment the effort stops, the ball comes up. So a Type 4 burst naturally fades. The trap leaks, the electrons cool, the structure shifts, and within hours, or at most a few days, the broadcast dies. That fade is not a flaw in the system. It is the expected behaviour. It is what these events do. There is a detail here worth slowing down for, because it tells you something about why scientists care about these bursts in the first place, beyond simple curiosity. The radio waves of a Type 4 burst are themselves completely harmless. They reach a spacecraft or a radio telescope as a faint signal, and they do nothing to us, nothing to our technology, nothing to anyone. You could not feel a solar radio burst if you tried. So at first glance you might wonder why anyone bothers to track them at all. And the answer is that the burst is not valuable as a threat. It is valuable as a marker. A Type 4 burst is a flag planted over a particular kind of place on the Sun. It says, here is a region with a complicated energized magnetic structure, a region that is trapping fast particles. And regions like that, magnetically complex and energetic, are also the regions most capable of producing the genuinely consequential space weather, the kind that can fling dangerous particles toward Earth, the kind that can affect satellites and spacecraft. So when scientists learn to read these bursts better, to identify them faster and locate them more precisely, they are not chasing a harmless curiosity for its own sake. They are sharpening a tool. They are getting better at recognizing early the kind of solar neighborhood that can turn dangerous. That is the practical thread running quietly underneath this entire record-breaking story, and it is worth keeping in the back of your mind, because it is the reason a burst that does nothing to us is still worth 19 days of 4 spacecrafts' attention, which means a 19-day Type 4 burst is not just a long version of a normal event. It is a violation of the normal event's basic nature. It is a beach ball that someone held underwater for 19 days, and the question that should be forming in your mind right now, the question that the scientists themselves had to confront, is the obvious one. If the trap naturally leaks, and the electrons naturally cool, and the broadcast naturally fades within days, then what on Earth, or rather what on the Sun, kept this one going for 19? Something had to be doing the work. Something had to be holding that beach ball down, and to find out what, the scientists first had to do something that sounds almost impossible. They had to figure out exactly where on the Sun this signal was coming from. We're going to get into that next, and the answer is a structure you have very likely seen with your own eyes, even if you never knew its name. Part 3. Finding the source. Here is a problem that sounds simple and is not. You have detected a radio signal coming from the Sun. The Sun is a sphere, an enormous glowing ball of plasma about 864,000 miles across. The signal is coming from somewhere on that sphere, or somewhere in the atmosphere just above it. Where, exactly? Point to it. It turns out that pinpointing the precise origin of a solar radio burst is genuinely difficult, and the difficulty is worth appreciating, because it explains why so much of this story is about technique rather than just observation. A radio burst is not like a bright spot you can photograph and circle. Radio waves are long, they spread out, they bend and scatter as they travel through this plasma of the Sun's own atmosphere on their way out. By the time the signal reaches a spacecraft, the information about exactly where it started has been smeared and blurred. You know the Sun is transmitting. Knowing which specific structure on the Sun is doing the transmitting is a far harder question. And for this particular event, the difficulty was multiplied by the problem we have already talked about. This source was moving. The Sun's rotation was carrying it across the disk the entire time. So scientists were not trying to locate a fixed point. They were trying to track a moving target across 19 days using fragmentary data handed off between multiple spacecraft. Most events do not force you to solve a problem like that. This one did, simply because it lasted long enough to make the Sun's rotation part of the puzzle. So the team did something clever. They developed a brand new technique, built specifically around data from one of NASA's spacecraft, a mission called STEREO. The name STEREO stands for Solar Terrestrial Relations Observatory, and the word stereo in the name is doing real work, because stereo was designed from the start around the idea of seeing the Sun from more than one angle, the same way your two eyes see the world from slightly different positions, and your brain fuses those two views into depth. Stereo's whole purpose in life is perspective, and the scientists studying this burst figured out a way to use Stereo's data to extract a location, to take the smeared, blurred radio signal and work backward to the specific region of the Sun it was emanating from. I am not going to pretend the technique is simple, because it is not, and the details are the kind of thing that fills a research paper. But the spirit of it is something you can absolutely grasp. It is triangulation. It is the same fundamental idea that lets you find something using more than one viewpoint. If you and a friend are standing in different spots, and you both point at the same distant bird, the two directions you're pointing will cross at exactly one place, and that crossing point tells you where the bird is. Your eyes do a version of this. Your phone's location services do a version of this with cell towers and satellites. The scientists did a version of this with the Sun's own radio signal, using Stereo's particular vantage point and a new analytical method to turn a vague direction into an actual address. It is worth appreciating why a new technique had to be invented at all, rather than just using whatever method already existed. Locating radio sources on the Sun is not a brand new problem. Scientists have been working on it for decades. But the standard approaches were largely built around events that behave the way ordinary bursts behave, events that are short-lived and stay roughly put. Those methods were not designed for a source that would spend 19 days being carried around a rotating star, observed in fragments by a shifting set of spacecraft. When you face a genuinely new kind of event, your old tools do not always stretch to fit it, and the honest scientific response is not to force the data into a method that was never meant for it. The honest response is to build a method that is. That is what the team did. They looked at the specific shape of this problem, a long-lived, moving, multiply-observed source, and they developed an approach, grounded in what Stereo in particular could provide, that was suited to that exact shape. The new technique is, in a sense, a piece of the legacy of this event that is just as important as the burst itself, because a method outlives the single case it was invented for. We will come back to that idea at the very end because it matters more than it might seem. Notice too that the rotation of the Sun, which was the great obstacle in this story, also quietly became an asset once the scientists had a way to handle it. A source that stays in one place gives you one viewing angle, and one viewing angle only. But a source that is carried around by the sun's rotation is, over time, presenting itself from a constantly changing angle. If you can track it through that motion, the rotation hands you a whole series of perspectives on the same structure, almost like slowly walking around a sculpture in a gallery instead of staring at it from a single fixed bench. The same fact that made the burst impossible for any one spacecraft to fully witness also, paradoxically, enriched what could be learned once the full picture was assembled. The obstacle and the gift were the same thing. It just depended on whether you had the means to use it, and when they followed that method through, when they pushed past the blur and pinned down where on the sun this 19-day broadcast was actually coming from, they landed on a structure with a name, a helmet streamer. Now, if you have never heard the term helmet streamer before, I want you to stay with me, because there is a very good chance you have already seen one. You may have seen one and not known what you were looking at, and once you know, you will never look at a particular kind of photograph the same way again. You know those photographs of a total solar eclipse, the ones where the moon has slid completely in front of the sun, and the sky has gone dark, and around the black disk of the moon there is this pale, structured, ghostly halo of light. That halo is the sun's corona, the sun's outer atmosphere, normally invisible to us because the blinding light of the sun's surface drowns it out completely. An eclipse is the one time we get to see it. The moon does the work of blocking the surface, and suddenly the faint, wispy, intricate corona stands revealed. It is worth pausing on just how strange and how lucky that is. The corona is always there. It surrounds the sun every second of every day. But the surface of the sun is so overwhelmingly bright that the corona, by comparison, is lost completely. The way the faint glow of a candle is lost if you hold it up next to a stadium floodlight. The only way to see the candle is to block the floodlight precisely, and the moon, by a coincidence of size and distance that has nothing to do with the sun's atmosphere at all, happens to be just the right apparent size to do exactly that, to cover the blinding surface and leave the faint corona exposed. For most of human history, a total solar eclipse was the only opportunity anyone ever had to study the structure of the sun's outer atmosphere directly. Generations of scientists planned entire expeditions, travelling to remote corners of the world just to get a few minutes of darkness in which to photograph the corona. And it was in those photographs, built up over many eclipses and many decades, that the structure of the corona was first mapped, and the streamers within it first recognised and named. The classic textbook image of a helmet streamer, the one that shows its shape most cleanly, comes from exactly this kind of eclipse photography, the long V-shaped form standing out against the dark sky. And if you look closely at one of those eclipse photographs, the corona is not a smooth, even glow. It has shape. It has structure. There are streamers, long pointed rays of light reaching outward from the sun in specific directions, often with a broad, rounded base close to the sun that narrows to a long, thin spike stretching far out into space. Some of those structures have a distinctive silhouette, a rounded dome at the bottom drawn up into a tapering point at the top. Scientists looked at that shape, that dome narrowing to a spike profile, and they thought it resembled the pointed helmets that soldiers wore in a previous century, and so they called it a helmet streamer. A helmet streamer is, physically, a large and long-lived magnetic structure in the sun's outer atmosphere. The rounded base of it is a region of closed magnetic field, those loops and arches of magnetism that leave the sun and curve back down into it. Plasma gets caught in that closed base, held there, glowing. And rising up out of that closed base is the long narrow spike, where the magnetic field gets stretched out and drawn into a thin extended sheet pointing away from the sun. Helmet streamers tend to form along the boundaries between regions of opposite magnetic polarity on the sun, the dividing lines between magnetic north and magnetic south, and they can be remarkably stable and persistent. They are not fleeting. They can sit there, holding their shape for a long time. Let me give you a slightly fuller picture of what a helmet streamer actually is, because the more clearly you can see it, the more the rest of this story snaps into focus. Picture the sun's surface, and picture two neighbouring regions of it, one where the magnetic field points outward, and one, right next to it, where the magnetic field points inward. Between any two regions of opposite magnetic polarity like that, the field has to do something to bridge the gap, and what it tends to do is form loops, arches of magnetism that rise out of one region, curve over, and come back down into the other. Now stack a great many of those loops together along the boundary, the smaller ones close to the surface and progressively larger ones above them, and you get a broad, rounded mound of nested closed magnetic arches. That mound is the base of the helmet streamer. Plasma gets caught inside those closed arches, held in place, and it glows, which is why the base of a streamer shows up as a bright, dense, rounded region in eclipse photographs. And then, above the mound, where the loops can no longer close because they have been stretched too far, the magnetic field gets drawn out into a long, thin, tapering blade that reaches far out into space. That is the spike. Dome of closed loops at the bottom, narrow spike at the top. A helmet. The crucial property for our purposes is that closed base. A closed magnetic loop is, almost by definition, a container. A charged particle threaded onto a closed loop runs along the loop, and, because the loop curves back on itself, it cannot simply escape into open space the way it could on an open field line. It is held. Now multiply that into the broad nested stack of closed loops at a helmet streamer's base, and you have something that is not just a single cage but a whole layered structure of cages, a region genuinely well suited to holding a population of energetic electrons in place. And helmet streamers are also, as solar structures go, unusually stable and unusually long-lived. They are not flickering, momentary things. They can hold their shape and their position for extended periods. So a helmet streamer brings two qualities to the table at once. It is a container, because of its closed base, and it is a persistent container, because of its natural stability. And I want you to notice how perfectly that description fits the mystery we have been building. We said a Type 4 burst is produced by energetic electrons trapped inside a closed magnetic structure. We said a 19-day Type 4 burst means a structure managed to hold its trapped electrons, radiating, for nearly 3 weeks. And now the source of this record-breaking burst has been pinned, through a brand new triangulation technique, to a helmet streamer, which is by its very nature a large, stable, long-lived structure with a closed magnetic base. The pieces are not just compatible, they are clicking together. The helmet streamer is exactly the kind of place where you would expect a population of electrons to be held still for a long time. It is a natural cage, a natural reservoir. But, and this is important, identifying the streamer does not finish the story, it deepens it. Because here is the thing, helmet streamers are common. They are a standard, well-known feature of the Sun's atmosphere. They are present somewhere on the Sun, essentially all the time. And yet a 19-day Type 4 burst had never been recorded before, not once in the entire history of this kind of observation. So if helmet streamers are ordinary, and helmet streamers are everywhere, then the streamer alone cannot be the whole answer. A helmet streamer is the container, it is the cage. But a cage, by itself, does not explain why this particular event ran 4 times longer than any event before it. An empty cage holds nothing. A cage with a leak slowly empties. Something had to keep filling this one. Something had to keep the reservoir topped up day after day for 19 days. The scientist had found where the energy was being held. They still had to find what kept feeding it, and the answer to that turned out to involve not one event but 3. Part 4. The Trio of Explosions. So we have our container, we have a helmet streamer, a large, stable, long-lived magnetic structure in the Sun's atmosphere, a natural cage with a closed magnetic base perfectly suited to trapping a population of energetic electrons. And we have established the problem with the container, which is that a container alone explains nothing. Helmet streamers are everywhere. Helmet streamers are always present. If a helmet streamer by itself could produce a 19-day radio burst, then 19-day radio bursts would be common, and they are the opposite of common. They had never been seen at all. So the scientist had to ask the harder question. What was different this time? What did this particular helmet streamer have during this particular 19-day window that no helmet streamer had ever been observed to have before? And when they examined the region of the Sun around the streamer during the event, they found their candidate. Not one thing. 3. During the window of the burst, the same region of the Sun that hosted the helmet streamer also produced a trio of coronal mass ejections, 3 of them. And the scientists' interpretation, the explanation they put forward in their published work, is that these 3 explosive outbursts are very likely what fueled the record. 3 eruptions from the same neighborhood, feeding the same trap. let us talk about what a coronal mass ejection actually is, because it is one of the genuine heavyweights of space weather, and you need to feel its scale to understand what it could do here. A coronal mass ejection, usually shortened to the initials, is an enormous eruption of plasma and magnetic field blasted off the Sun. We are not talking about a little puff of gas. We are talking about a cloud of charged particles that can contain billions of tons of material, launched off the Sun and out into space at speeds that can reach millions of miles per hour. When a coronal mass ejection is aimed at Earth, it is the thing that drives the big geomagnetic storms, the events that light up the sky with auroras far from the poles and, in the strongest cases, can stress power grids and disrupt satellites. A coronal mass ejection is the Sun throwing a genuine punch. It also helps to know where coronal mass ejections come from, because that connects directly to why 3 of them clustered in one place. The Sun's atmosphere is laced with magnetic energy, and in some regions that energy gets wound up, twisted and stressed, like a spring being compressed or a rubber band being twisted tighter and tighter. A region of the Sun with a particularly complicated knotted magnetic configuration is a region storing a lot of strain, and stored magnetic strain does not stay stored forever. Eventually the configuration becomes unstable, the magnetic field snaps into a simpler arrangement, and the energy that was locked up in the twist gets released, violently, all at once. That release is what powers solar flares, and it is what launches coronal mass ejections. So eruptions are not random sprinkles across the Sun's face. They cluster in the magnetically complicated regions, because those are the regions with strain to release. A single region that is knotted and energetic enough can produce eruption after eruption as it works through its stored stress. And that is precisely the situation our helmet streamer found itself in. It was not sitting in a calm neighbourhood that happened to get struck by lightning 3 times. It was sitting in, or right beside, a magnetically loaded region that was actively capable of firing off a series of eruptions. The trio of coronal mass ejections was not 3 separate strokes of bad luck. It was one energetic region behaving the way an energetic region behaves, and the helmet streamer just happened to be perfectly positioned to be refueled by every shot it fired. Now, the 3 coronal mass ejections involved in this story were not the headline here. They were not aimed at Earth in a way that produced some dramatic terrestrial event. Their importance is not what they did to us. Their importance is what they did to the helmet streamer sitting right there in the same region of the Sun. And to understand that, I want to go back to the image we have been using, the beach ball held underwater. We said that a Type 4 burst naturally fades. The trapped electrons leak out at the edges of the magnetic structure. They collide and cool and lose energy. The radiating itself drains them. Left completely alone, a magnetic trap full of energetic electrons empties out within hours, or at the very most a few days, and the broadcast dies. That is the beach ball wanting to come up. The natural state of the system is fade. So to keep a Type 4 burst going for 19 days, something has to actively fight that fade. Something has to keep doing work. And the scientist's picture is that the 3 coronal mass ejections were that something. Each eruption, blasting off from the same region, did something useful for the trap. There are a couple of ways an eruption like that could help, and the honest scientific position is that it was probably some combination of them. One possibility is that each coronal mass ejection reorganized the large-scale magnetic structure, reshaping and reinforcing the cage itself, effectively rebuilding the walls of the container before they could fully collapse or leak away. Another possibility is that each eruption injected a fresh batch of energetic electrons up from the lower atmosphere of the Sun into the trap, refilling the reservoir with new particles to replace the ones that had drained or cooled. Reinforcing the cage, refilling the reservoir, quite possibly both. The exact details are the kind of thing that research papers are written to work out. But the central idea is clean, and it is satisfying, so let me state it as plainly as I can. The helmet streamer was the container. It was a good container, a stable one, but on its own it would have leaked empty within days, the way every Type 4 burst before it had. What made this event a record breaker was that the container kept getting refueled. 3 times, over the course of the event, a coronal mass ejection erupted from the same region and topped the system back up, reinforced the walls, refilled the tank, and as long as the refueling kept happening, the trapped electrons kept radiating and the burst kept going. I find it useful to think about the timing here, because the timing is really the whole secret. Imagine you have established that a magnetic trap left alone drains in something like 5 days. That 5-day figure is, after all, roughly where the old records sat, and it is a reasonable stand-in for how long one of these systems can coast on a single loading. Now imagine an eruption sets the trap up and gets it broadcasting. The clock starts. The system begins its slow drain. If nothing else happens, you get an event of around the old record's length, and then silence. But suppose that before the drain completes, a second eruption arrives, and it reloads the system. The clock effectively resets. The drain starts over from full, and suppose that before that second loading runs out, a third eruption arrives and reloads it again. What you have built, with just 3 well-placed eruptions, is not a 5-day event and not a 15-day event, but something that can run substantially longer than the simple sum, because each reload does not just add time, it restores the system to a state from which it can coast again. 3 eruptions, correctly spaced, can hold a broadcast alive across a span that no single one of them could come close to producing. The 19 days were not 3 separate 5-day events laid end to end. They were one continuous event, kept continuous, because the gaps between reloads never grew long enough for the trap to fully empty and go dark. And the spacing is exactly why this is so rare. The eruptions could not come all at once, because then they would simply load the trap heavily one time, and you would still get only one drain cycle. They could not come too far apart, because then the trap would empty between them, and the burst would break into separate shorter events instead of one record breaker. They had to arrive within a window, spaced closely enough to keep the system from ever going dark, but spread out enough to each count as a fresh reload. 3 eruptions from one region, falling into that specific rhythm. That is not the kind of thing that happens often. That is the kind of thing that happens when a great many independent factors line up by chance, and it is the reason a 19-day burst had never been recorded before, even though every individual ingredient in it is something the sun does routinely. It was not one event stretched impossibly long. It was a relay, a handoff. A first eruption sets the system up and gets it broadcasting. The broadcast starts to fade the way it always does. A second eruption arrives and tops it back up before it can die. The broadcast fades again. A third eruption arrives and refuels it once more. 19 days of continuous radio emission, not because any single thing lasted 19 days, but because the sun in this one region happened to fire off a sequence of explosions perfectly timed and perfectly placed to keep one helmet streamer's trap loaded. And once you see it that way, the event stops being a single impossible thing and becomes a chain of ordinary things that lined up extraordinarily well. A helmet streamer is ordinary. The sun has them constantly. A coronal mass ejection is ordinary too, especially when the sun is in an active phase, which it has been. The sun has been a busy, eruptive star lately. Coronal mass ejections from active regions are part of the normal weather, so none of the individual ingredients here is exotic. What was rare, what had never been caught before, was the alignment. The right container, in the right place, getting refueled by the right number of eruptions with the right timing from the right region for long enough to run the duration out to 19 days. This is honestly one of the most common shapes a genuinely remarkable event takes, and it is worth recognizing the shape because once you can see it, you will see it everywhere. The most extraordinary outcomes in nature are very often not produced by one extraordinary cause. They are produced by a stack of ordinary causes that happen by chance, to line up in just the right way at just the right time. Each individual piece is mundane. The pile-up is what is rare. A helmet streamer, a coronal mass ejection, a region magnetically complex enough to fire repeatedly, the rotation of the sun carrying the source across a fleet of watching spacecraft. None of those is unusual on its own. Every one of them is something the sun or the solar system does as a matter of routine. The 19-day burst is what you get when all of those routine things happen to coincide. And that is a genuinely important idea to carry around, because the dramatic, ominous reading of events like this one depends entirely on you not seeing it. The ominous reading needs the event to have a single, hidden, extraordinary cause. The truth is almost always less sinister and, frankly, more elegant. A rare result does not require a rare kind of cause. It only requires ordinary causes to align. There is one more thing I want to flag before we move on, and it is a point about scientific honesty. Notice that I have been careful, throughout this part, to say that the 3 coronal mass ejections may have fueled the event, that they plausibly sustained the trap. that the exact mechanism is some combination of reinforcing the cage and refilling the reservoir. I have not said the scientists proved every detail with total certainty, and that careful, slightly hedged language is not a weakness in the story. It is the story being told honestly. The scientists located the source with confidence. They identified the trio of eruptions with confidence. The precise step-by-step physics of how each eruption sustained the trap is the part that is still being refined, and the researchers said so plainly. That is what real science sounds like. It states clearly what it knows, marks clearly what it is still working out, and does not paper over the difference. When you encounter a version of a science story that has no hedges at all, where every detail is presented as absolute certainty, and the whole thing is wrapped up with a bow, that confidence should make you more suspicious, not less. The real account, with its careful distinctions between what is settled and what is still open, is the trustworthy one. This is the place in the story where I want to be very direct with you, because the title of this video makes a strong claim, and you deserve precision about exactly which part of it is true. The sun did do something we have never seen before. That is real. A 19-day Type 4 radio burst had never been recorded. The previous record was 5 days, and this nearly quadrupled it, and that is genuinely unprecedented in the history of this kind of observation. So the headline is not hype. The sun broke a record by a margin that should make anyone sit up. But notice what the scientists did not say. They did not throw up their hands. They did not say this is beyond explanation, or this makes no sense, or we have no idea what happened. They said the opposite. They identified the container. They located it, using a brand new technique, as a specific helmet streamer. They identified the likely fuel. They named 3 coronal mass ejections from the same region, and laid out how those eruptions could have sustained the trap. And then they published the whole analysis in a peer-reviewed scientific journal, the Astrophysical Journal Letters, so that other scientists could check it, challenge it, and build on it. That is not the behavior of people staring at something inexplicable. That is the behavior of people who did the detective work and solved the case. And I think it is worth being honest about why that distinction matters, because a story like this one travels fast, and when it travels, it tends to mutate. A record-breaking solar event is exactly the kind of thing that gets picked up online and reshaped, and the reshaping almost always pushes in the same direction, from record-breaking toward unexplainable, from rare toward ominous, from the sun did something surprising toward the sun is doing something nobody can account for, and nobody is telling you about. We are going to deal with that version of the story head-on later in this video, because it deserves a direct and fair answer rather than a sneer. But I want to plant the flag now, while the science is fresh in your mind. Longer than ever recorded is true. Beyond explanation is not. The sun broke a record. It did not break the laws of physics, and the people whose job is to understand our star did exactly that. They understood it. So if the science is, in its broad strokes, solved, you might wonder what is left. Why a whole video? And the answer is that the most remarkable part of this story is not actually the burst, it is how we caught it. Because solving this case required something that, just a couple of decades ago, would not have been possible at all. It required a fleet. It required 4 separate spacecraft scattered across the inner solar system, passing a single signal between them like runners in a relay. And that, the human side of this, the machinery and the ingenuity that turned a moving, fragmentary, 19-day signal into a solved scientific case, is where we are going next. Part 5. The relay race across the solar system. I want to step back from the sun for a moment and talk about us, because so far this video has been a story about our star, about magnetic cages and trapped electrons and a trio of explosions. But there is a second story braided through this one, and it is a story about human beings and machines we built, and a problem we solved that we would not have been able to solve in any previous era. And honestly, it might be the part of all this that I find most moving. Remember the core difficulty. This burst lasted 19 days, and the sun rotates, so the source of the burst was not sitting still. It was being carried steadily across the face of the sun and around the edge by the rotation of the star itself. We compared it earlier to trying to photograph a marathon runner through a window that only shows you one block of the course. No single observer can see the whole race. The runner enters your window, crosses it, and exits, and after that the runner is somewhere you simply cannot see, while the race goes on without you, So if you want the whole race, you cannot rely on one window. You need windows all along the route. You need observers stationed at different points, each one watching their own stretch, each one picking up the runner as the previous observer loses sight of them. And that is precisely what the science of this event required, except the route was a path around the sun, and the observers were spacecraft, and the stretches they each covered were measured in days. 4 missions made this possible. I want to introduce them properly because each one is a remarkable machine in its own right, and the fact that all 4 happened to be in the right places at the right time, ready to hand this signal off between them, is not something to take for granted. The first is Stereo, the Solar Terrestrial Relations Observatory, the mission we have already met, the one whose data became the basis for the new source location technique. Stereo was built around the principle of seeing the sun from a vantage point other than Earth's, and that off-to-the-side perspective is exactly what made it possible to triangulate the burst, to turn a blurred signal into an actual location on the solar disk. Stereo was, in a sense, the spacecraft that let scientists point at the bird from a second angle. The second is Parker Solar Probe, and Parker is frankly one of the most extraordinary machines humanity has ever flown. Parker Solar Probe is the spacecraft that goes to the sun. It does not just observe the sun from a comfortable distance. It dives in, repeatedly swinging closer to the sun than any spacecraft in history, flying through the outer reaches of the sun's own atmosphere, protected by a heat shield against temperatures that would destroy almost anything else we have ever built. Parker is the closest human-made object to our star, and for this event it contributed observations from far inside the inner solar system, a vantage point no spacecraft before it could ever have offered. The third is Wind. Wind is one of the quiet veterans of space science, a mission that has been monitoring the solar wind, the constant stream of charged particles flowing off the sun, for a very long time. It does not get the headlines that Parker gets, but it is a reliable, long-serving sentinel, and it added another set of eyes, another vantage point, another stretch of the route covered. And the fourth is Solar Orbiter, a mission flown jointly by the European Space Agency and NASA, a genuinely international machine designed to study the sun up close and from angles that let it see parts of our star that are hard to observe from the plane the Earth orbits in. Solar Orbiter contributed yet another independent line of sight, another window on the route. 4 spacecraft, Stereo, Parker Solar Probe, Wind, and Solar Orbiter, spread out across the inner solar system, sitting at different points, looking at the sun from different angles. And for 19 days, as the sun's rotation carried the burst source along its slow path, these 4 machines passed the observation between them. One spacecraft would have the source in view, watching it, recording it for a few days. Then the rotation would carry the source out of that spacecraft's view, and another spacecraft, positioned elsewhere, would pick it up and carry the watch forward. A few days here, a handoff, a few days there, another handoff. A relay race, run not by people but by spacecraft, around a star, with a record-breaking radio signal as the baton. And I want you to really sit with how improbable and how wonderful that is. No one launched these 4 missions as a team. They were not designed together as a single coordinated burst tracking system. Stereo, Parker, Wind, and Solar Orbiter were each conceived, built, and flown for their own reasons, their own primary science goals, their own missions. They just happened to all be operating at the same time, and they happened to be distributed across the inner solar system in a configuration that, when this 19-day burst occurred, allowed them to collectively see the whole thing. The relay was not planned. It was assembled, after the fact, by scientists who realized that the fragments these 4 spacecraft had each independently recorded could be stitched together into one continuous, unbroken 19-day story. Let me make the geometry of that a little more concrete, because the phrase scattered across the inner solar system can wash over you if you do not pause on it. The inner solar system is not a small place. It is the region containing the orbits of the rocky planets, and a spacecraft sitting at one point in it can be many tens of millions of miles away from a spacecraft sitting at another. When you have 4 machines distributed through that volume, each one is looking at the sun from a genuinely different direction, and the sun presents a genuinely different face to each of them. A feature that is squarely visible to one spacecraft can be completely hidden around the curve of the sun from another, and that is exactly the property that makes a relay possible. Because the source of this burst was rotating with the sun, It was always, at any given moment, on the visible side for some of these spacecraft and the hidden side for others. As the rotation carried it along, it would slip off the edge of one spacecraft's view and, at roughly the same time, come around into another's. The handoffs were not arranged by mission controllers radioing each other. They were arranged by orbital geometry, by the simple fact that 4 observers spread around a sphere will, between them, always have eyes on every part of it. The scientist's job was to recognize that this had happened and to assemble the pieces correctly. And there is something else about this fleet that deserves a moment, which is the sheer range of conditions these 4 machines were built to survive. Parker Solar Probe endures heat that would obliterate an unprotected spacecraft, because its job is to fly through the sun's outer atmosphere. Wind has simply endured time, operating as a steady monitor for far longer than most missions are designed to last. Solar Orbiter was engineered to climb out of the flat plane that the planets orbit in, so it can look down on regions of the sun that are awkward or impossible to study from near the Earth. Stereo was built to deliver perspective, the off-axis viewpoint that makes triangulation work. 4 different design philosophies, 4 different sets of engineering compromises, 4 different primary purposes. And the 19-day burst needed all of them. It needed Parker's closeness, and Wind's endurance, and Solar Orbiter's vantage and Stereo's perspective, not because anyone planned for that, but because an event this long and this mobile happened to demand exactly the combined coverage that this particular set of machines, by luck and by decades of accumulated investment, was able to provide. That stitching is itself a real achievement, and it is worth not glossing over. It is not trivial to take observations from 4 different machines, each with its own instruments, its own position, its own perspective, its own quirks, and combine them into a single coherent record. It is painstaking work. It is calibration and cross-checking and making sure that what one spacecraft saw genuinely connects to what the next one saw, that you are following one continuous event and not accidentally splicing together 2 different things. The 19-day burst, as a single documented phenomenon, did not fall out of the sky as a finished fact. It was constructed carefully by people, out of pieces. And this is why I said earlier that the most remarkable part of this story might not be the sun at all. The sun, in the end, did something dramatic but explicable. It built a magnetic cage and an alignment of eruptions refueled it for 19 days. That is a real event, and it broke a real record. But the catching of it, the documenting of it, the turning of it from an unnoticed signal into a solved and published case, that required a level of capability that simply did not exist for most of the history of solar science. A fleet of spacecraft scattered across the inner solar system. A new analytical technique invented to extract a location from a moving source. International cooperation, with a European and American mission flying side by side. Decades of investment in machines that watch the sun. All of it came together, none of it planned for this specific event, to let a handful of scientists reconstruct 19 days in the life of our star. Think about what this same burst would have been in an earlier era. 50 years ago, 60 years ago, a burst like this would not have been a record breaker. It would not have been anything. It would have been, at best, a partial observation from a single ground-based radio telescope, a few days of signal, and then nothing, because the source would have rotated out of view, and there would have been no second window, no third, no fourth, to follow it. The event would have happened exactly as it happened in 2025. The sun does not care what instruments we have. But we would never have known. The 19-day burst would have been a 5-day burst in our records, or a 2-day burst, or simply an unremarkable blip because our ability to see only extended as far as one window. There is something almost humbling in that, and I do not want to rush past it. We tend to assume that our records of the natural world are records of the natural world. We assume that when we say the longest such event lasted 5 days, we are stating a fact about the events. But a record is really 2 things layered on top of each other. It is partly a fact about what nature did, and it is partly a fact about what we were able to observe. And for most of the history of solar physics, those 2 things were impossible to separate cleanly, because our observing was limited enough that we could never be sure whether we were measuring the sun or measuring our own reach. The fleet changes that. With 4 spacecraft providing genuinely complete gap-free coverage of a rotating source, scientists can finally be confident for an event like this one that they measured the event itself and not the edge of their own window. The 19-day figure is trustworthy in a way that earlier numbers, through no fault of the earlier scientists, simply could not be. It is one of the first solar radio burst durations in history that we can be confident reflects the sun, and not the limit of the telescope, and that realization should make you look back at the old 5-day record with fresh and slightly skeptical eyes. We have been treating it throughout this video as the previous record, the thing that got beaten. But ask yourself what that 5-day number actually was. It was the longest such burst that had been observed and documented. It was never a guarantee that the sun could not do more. It was a high water mark of human observation, as much as a high water mark of solar behaviour. And once you frame it that way, the 19-day burst stops looking quite so much like the sun suddenly leaping past a natural limit, and starts looking more like the moment our observation finally caught up enough to see past an artificial one. Which brings us to a question we cannot avoid any longer. Before we get to that question, I want to give the human side of this its full due, because it is easy to say 4 spacecraft and move on, and that phrase hides an enormous amount of work. Every one of those 4 missions represents years of design, of testing, of engineering arguments settled and budgets defended and launch windows met. Every one of them represents teams of people, many of whom will never be named in any headline, who built the instruments, who fly the spacecraft day after day, who keep the aging ones alive long past their original mission plans, who maintain the archives where the data lives, and the new analysis technique represents its own quieter labour, the unglamorous, painstaking work of taking a hard problem and inventing a method to crack it. When you read that scientists tracked a record-breaking burst around the sun, you are reading the visible tip of all of that. The burst lasted 19 days. The capability that caught it took decades to assemble. That asymmetry, a brief event caught by a long, patient, collective human effort, is worth holding on to because it is the real texture of how discoveries like this actually happen. They are not lightning strikes of genius. They are the moment when a long, slow, shared investment finally meets an event worthy of it. And that thought leads directly to one of the most genuinely interesting questions this whole story raises, a question we are going to take seriously in the next part. If our ability to catch an event like this is so recent, so dependent on having a fleet in the right place, then how do we actually know this is rare? How do we know the sun has not been doing this, or something like it, for a very long time, while we simply lacked the eyes to notice? Is this a new behaviour from our star, or is it an old behaviour, and what is actually new is us? Part 6. Is the sun changing, or are we just watching better? This is the question I find genuinely fascinating, and it is the question that sits right at the boundary between solid science and honest speculation, so I want to handle it with care. We have a record-breaking event, a 19-day Type 4 solar radio burst against a previous record of about 5 days. The instinct when you hear that is to assume the sun did something new, something changed. Our star produced a behaviour it had not produced before, and maybe that is true, but there is a second possibility, and it is just as interesting and it might be more likely, and it is this. Maybe the sun has been capable of 19-day bursts all along. Maybe it has produced them before, more than once, perhaps many times. And maybe the reason this is the first one in the record books is not that the sun changed, but that we did. Let me make the case for that second possibility, because it follows directly from everything we covered in the last part. We just spent an entire section establishing that catching this event required 4 spacecraft, scattered across the inner solar system, passing the observation between them as the sun's rotation carried the source around. We established that no single observatory could have seen the whole thing, because the source moved out of any one window within days, and we established that this kind of multi-spacecraft, full coverage capability is recent. It is a feature of this specific era of space science, not of all of history. So now run the logic forward. If catching a 19-day burst requires a relay of spacecraft positioned all the way around the inner solar system, and if that relay capability has only existed for a relatively short slice of time, then what would have happened to a 19-day burst that occurred before that capability existed? The answer is simple and a little haunting. It would have been recorded as a short burst. An observer with a single window would have watched the source for the few days it was in view, logged a burst of that length, and then lost it. The remaining 2 weeks of the event would have happened, out of sight, around the far side of the sun, completely undocumented. In our records, a 19-day burst from 1970 or 1980, or even much more recently, might appear as a 4-day burst or a 5-day burst. It might appear as exactly the kind of event that set the old record. Do you see what that means? It is genuinely possible that the old record of 5 days was never really a record of how long these bursts last. It may have been a record of how long we were able to watch. The 5-day ceiling might have been a ceiling on our observation, not a ceiling on the sun's behaviour, and the 19-day event might not be the sun doing something new at all. It might simply be the first time our eyes were good enough and numerous enough and well placed enough to follow one of these bursts all the way to its real end. This is a known and respectable problem in science, and it has a name. It is broadly an observational bias, or a selection effect. It is the trap of mistaking a limit of your instruments for a fact about nature. The history of astronomy is full of moments where humanity built a better instrument, and suddenly the universe seemed to fill up with things that were, in truth, always there. We did not create those things by looking. We just finally saw them, and it is entirely plausible, maybe even probable, that long-duration solar radio bursts belong in that category, that the sun has been quietly producing them for as long as it has been a star, and that 2025 is simply the year we happen to be watching closely enough, with enough spacecraft in enough places to catch one in full. Consider how many separate things had to be true, all at once, for this event to make it into the record at all. A burst of this duration had to occur. 4 capable spacecraft had to be operating simultaneously. Those 4 spacecraft had to be distributed around the inner solar system in a configuration that, between them, kept the rotating source in view across the whole 19 days. A team of scientists had to be paying enough attention to notice that something unusual was running. That team had to have, or be able to invent, a technique capable of pulling a location out of the data, and then the painstaking work of stitching the fragments together had to actually get done. Remove any one of those conditions and the 19-day burst as a documented fact evaporates. The event still happens up on the sun exactly as it happened, but it never reaches us as knowledge. Now think about how recently all of those conditions became possible to satisfy together. The honest conclusion is that the window in which humanity can catch an event like this is narrow and new, and whenever the window for catching something is narrow and new, you should be deeply cautious about treating the first catch as the first occurrence. Those are not the same claim. The first time you photograph a rare animal is not the day the animal came into existence. Now, I want to be fair to the other side of this because honesty cuts both ways. The observational bias explanation is compelling, but it is not the only possibility, and the scientists themselves have not declared the question closed. There is a real, genuine version of the alternative where this event reflects something specific about the state of the sun right now. We have mentioned that the sun has been in an active phase. The sun runs on a roughly 11-year cycle of rising and falling activity, swinging from quiet stretches with few sunspots and few eruptions to busy stretches crowded with sunspots, flares, and coronal mass ejections. And the current cycle has been, by a number of measures, more active than was predicted. A more active sun produces more coronal mass ejections, and our explanation for the 19-day burst depended entirely on a trio of coronal mass ejections from one region refueling the trap. So it is reasonable to ask whether an unusually active sun makes the right kind of multi-eruption sequence more likely, whether the conditions for an extreme long-duration burst are simply more available right now than they are during a quiet phase. Under that reading, the event is not purely an observational fluke. It is partly a product of the particular energetic mood our star is in at this moment in its cycle. So which is it? Is the 19-day burst a behaviour the sun has always had and we only just caught? Or is it a behaviour made more likely by the sun's current activity? Or is it some genuine combination of both? And the honest grown-up answer, the one the science actually supports, is that we do not yet know for certain, and that is not a disappointing answer. It is the exciting one, because it means the 19-day burst is not a closed case to be filed away. It is a doorway. It is the first solidly documented example of something, and the existence of one well-studied example is what makes it possible to go looking for more, and that is exactly what the new technique is for. Remember, the scientists did not just study this one event. They built a new method, grounded in stereo data, for pinpointing the source of a radio burst. That method does not expire when this paper is published. It becomes a tool. It becomes part of the standard kit. And with that tool in hand, scientists can go back through old data and look again and they can watch new bursts as they happen with sharper eyes. Over the coming years, that is how this question gets answered. If long-duration bursts start turning up regularly, now that people know how to look for them and have the technique to track them, that will strongly suggest the sun was doing this all along and we were simply missing it. If on the other hand they stay genuinely rare even with the new tools and the watching fleet, that will suggest the 19-day event really was an exceptional alignment, a rare confluence of the right streamer and the right eruptions, and that will tell us something important too. There is one more reason this matters, and it brings us back to that practical thread we touched on earlier. Better identification of these bursts is not just about satisfying curiosity. The scientists were explicit that part of the value of this work is improved space weather forecasting. Remember why. A long-lived Type 4 burst is a flag over a magnetically complex eruption-prone region of the Sun, and those are exactly the regions that can produce the kind of solar activity that sends dangerous energetic particles toward Earth, the kind that can affect satellites and spacecraft. We live in an era that depends on a fragile shell of technology orbiting our planet, satellites for navigation and communication and weather and observation, and that technology is genuinely vulnerable to severe space weather. So a tool that helps scientists recognize a dangerous solar neighborhood faster and pin down where it is more precisely has real protective value. The 19-day burst, for all its strangeness, fed directly into something useful. The same investigation that broke a record also sharpened our ability to read the warning signs of the solar activity that actually can reach out and touch the systems we rely on. Either way, the 19-day burst has done the most valuable thing a scientific event can do. It has turned a vague question into a sharp one, and it has handed scientists the instrument to chase the answer. We started this video with a signal that nobody thought was interesting. We are now standing in front of an open, well-posed, genuinely profound question about our own star, a question we now have the means to investigate. That is what good science feels like from the inside, not a tidy ending, a better beginning. But there is another version of this story circulating out there, a version that does not end in a better beginning. It ends somewhere darker, and it travels faster than the careful version ever could. And because it does travel fast, and because some of you have very likely already encountered it, I'm not going to pretend it does not exist. We're going to look at it directly and fairly next. Part 7. When a record becomes a rumour. Let us talk about what happens to a story like this once it leaves the scientists' hands. Because a 19-day record-breaking event from the Sun does not stay in a quiet corner of a research journal. It gets out. It spreads. It moves across the internet, across social feeds, across videos and posts and comment threads. And as it moves, it changes. That is not a conspiracy. That is just what happens to information when it travels through a lot of human beings. Every retelling shaves off a little nuance and adds a little drama, and after enough retellings, the careful scientific finding has quietly transformed into something else. And the direction it transforms in is almost always the same. It moves from record-breaking toward unexplainable. It moves from rare toward ominous. It moves from the Sun did something surprising, and scientists figured it out toward the Sun is doing something strange, and nobody can explain it, and maybe nobody wants you to think about it too hard. I want to walk through that transformation honestly, because the worst way to handle the alternative version of a story is to mock the people who believe it. The best way is to take the real concern seriously, give it a fair hearing, and then show carefully exactly where it goes wrong. So let us start with what the alternative version gets right, because it does get something right, and pretending otherwise would be dishonest. The core observation at the centre of the online conversation is accurate. The Sun did break a record, and it broke it by a wide and startling margin. 19 days against a previous best of 5 is genuinely surprising. Anyone who looks at that and feels a little jolt of unease is responding to something real. The surprise is not manufactured. The event is, by the standards of this kind of solar science, extraordinary. So if you have seen this story online and felt that something significant happened, you were not wrong. Something significant did happen. That instinct is sound. The trouble begins with the next step. The leap that the alternative version makes, almost always, is the leap from record-breaking to unexplainable. It takes the genuine fact that this was the longest such burst ever recorded, and it quietly swaps in a different claim, that this was a burst nobody can account for. And those two statements are not the same. They are not even close to the same. One of them is true and the other is false, and the entire credibility of the dramatic version depends on you not noticing the swap. Here is the correction, stated as plainly as I can state it. This event is not unexplained. We spent the core of this video on the explanation, and it is a real one, and it was arrived at by real scientists doing real work. The source was located through a brand new triangulation technique to a specific helmet streamer, a known and ordinary type of solar structure. The fuel was identified as a trio of coronal mass ejections from the same region, repeatedly refueling the trapped electron population. The whole analysis was written up and published in a peer-reviewed scientific journal, the Astrophysical Journal Letters, which means it was checked by other scientists before it ever reached the public. That is not what an unexplained event looks like. An unexplained event does not come with a located source, an identified energy supply, and a published mechanism. This event came with all three. It is, in the ways that matter, solved. The honest word for it is not unexplained. The honest word is unprecedented, and those two words mean very different things. Unprecedented means it had not happened in our records before. Unexplained means we do not know why it happened. This event is the first. It is emphatically not the second. Now there is a second, larger claim that often gets attached to this story, and I want to address it directly and respectfully, because it is more ambitious and it requires a more careful answer. The larger claim goes something like this. The 19-day burst is not an isolated oddity. It is one symptom among many. The Sun, the argument goes, has been behaving strangely across the board, and if you stack this burst together with other reported solar curiosities, a pattern emerges, and that pattern points to some deeper change. And in the more elaborate versions, that deeper change gets linked to the space beyond the Sun entirely, to ideas about a shifting local galactic magnetic environment, a galactic current sheet, the notion that the whole solar system is moving into some new, external magnetic region, and that everything from the Sun to the Earth is being affected. I want to be careful and fair here, because there is a real branch of science tangled up in that claim, and I am not going to wave it away. It is genuinely true that the Sun sits inside a larger environment. The Sun produces an enormous bubble called the heliosphere, inflated by the solar wind, and that bubble pushes out against the interstellar medium, the thin material that fills the space between the stars. The boundary region where the heliosphere meets interstellar space is a real place. It is genuinely studied, and the interaction between our solar system and its galactic surroundings is a legitimate and active field of heliophysics. Spacecraft have actually crossed that boundary, so if someone tells you the Sun has an interstellar environment and that scientists study it, they are correct. That part is not fringe at all. The problem is the connection. The problem is the line that the dramatic version draws between that real, large-scale heliophysics and this specific radio burst. Because that line does not exist in the science. The 19-day burst was not explained by anything galactic. It was not explained by a current sheet, or by an interstellar magnetic shift, or by the solar system moving into a new region of space. It was explained by processes happening on the Sun itself, a helmet streamer in the Sun's own atmosphere, coronal mass ejections from a single active region on the Sun's own surface. The explanation is entirely local to our star. To take this burst and present it as evidence of a galaxy-scale magnetic transformation is to attach a small, well-understood solar event to an enormous claim it simply cannot support. The burst does not point outward to the galaxy. Everything about its documented cause points inward, to the Sun. And there is a softer version of all this that I think deserves the gentlest answer of all, because it is less a theory and more a mood. It is the feeling, expressed in a lot of these conversations, that the Sun just seems off lately, that there have been a lot of strange solar headlines, and this burst is one more, and surely all of it together must mean something is wrong. I understand that feeling. I genuinely do. But here is the calm, grounded response to it. The Sun is a variable star. It is supposed to change. It runs on that roughly 11-year cycle, swinging between quiet and active, and right now it is in an active stretch. A stretch that has actually run a bit hotter than forecasters predicted. An active Sun produces more flares, more coronal mass ejections, more of everything dramatic and therefore more dramatic headlines. A run of dramatic solar news is not, by itself, evidence that something is wrong. It is, much more simply, what an active phase of a normal star's cycle looks like when there is a fleet of spacecraft watching it, and a global media ready to report every event. More headlines is partly a fact about the Sun, and partly a fact about us watching harder than we ever have. Let me put a finer point on that, because the 11-year cycle is genuinely the most important context for the whole soft version of the fear conversation. The Sun has been running this cycle for as long as humans have kept records of sunspots, and well beyond. It is one of the most reliable patterns in all of solar science. The Sun gets busy, then it gets quiet, then it gets busy again, on a rhythm of roughly a decade. During the busy stretches, the Sun is supposed to be eruptive. It is supposed to throw flares and coronal mass ejections. That is not the Sun breaking. That is the Sun doing the single, most well-documented thing it does. And when you also remember that this particular active stretch has run somewhat stronger than was forecast, the picture becomes even clearer. We have a Sun that is in the loud part of its cycle, and a little louder than expected, being watched more closely and more continuously than at any point in human history, by more instruments, with the results carried instantly to a global audience. Of course, there are a lot of dramatic solar stories right now. The conditions for producing dramatic solar stories, both the solar conditions and the human ones, are all simultaneously elevated. A flood of dramatic headlines under those circumstances is the expected outcome, not an anomaly that demands a sinister explanation. There is also a subtle but important point about how a mood like this sustains itself, and I say this with no judgment, because every single one of us is vulnerable to it. When you start with the feeling that something is wrong, every new headline gets quietly sorted into the pile that confirms it. A record-breaking burst, a strong flare, an unusual reading, each one feels like another brick in the wall. But the headlines that would push the other way, the ordinary days, the quiet stretches, the events that turned out to have tidy explanations, those do not get added to the pile, because they do not feel like evidence of anything, they just feel like nothing. And so the pile only ever grows in one direction, not because the Sun is only ever doing alarming things, but because alarming things are the only things that get counted. The honest correction is not to dismiss the alarming events, it is to also count the ordinary ones, and to remember that a fully explained, peer-reviewed, record-breaking burst belongs much more in the column of science working than in the column of something is wrong. And genuinely rare events do happen. That is not a loophole. That is how reality works. Records exist to be broken, and occasionally one of them breaks by a lot. A 19-day burst, fully studied and fully published, is not a crack in our understanding of the Sun. It is a demonstration of our understanding of the Sun. It is the system working. An event landed at the far edge of what was thought possible, and the scientific machinery, the spacecraft and the techniques and the peer review did exactly what it is built to do. It caught the event, it located the source, it identified the cause, and it put the result on the public record for anyone to examine. I want to add one more thought here, because there is a question that naturally arises and it deserves a straight answer. Someone might say, fine, but how do you know the scientists got it right? How do you know the helmet streamer and the 3 eruptions are the real explanation and not just a comfortable story? And that is a completely fair question, the right kind of skepticism to bring to anything. The answer is in the process. This finding was not announced by a single person on a stage with no way to check it. It was written up in detail and submitted to a peer-reviewed scientific journal, which means that before it was ever published, other scientists, experts in this field who were not part of the original team, read the analysis, examined the reasoning, looked for holes, and judged whether the conclusion was supported by the data. That process is not perfect, no human process is, but it is specifically designed to catch exactly the kind of error that a comfortable but wrong story would contain. And beyond that first round of review, publication is itself an invitation. By putting the analysis on the public record, the team has handed it to the entire global community of solar physicists and effectively said, here is our reasoning, test it, challenge it, try to break it. If the helmet streamer and the eruption refueling picture were wrong, the way to find out is precisely to publish it and let everyone else take a swing. So when I say this event is explained, I do not mean one team feels confident. I mean the explanation has entered the open, adversarial, self-correcting machinery of science, and that machinery is the best tool humanity has ever built for separating what is true from what is merely appealing. So here is the line I want you to carry out of this part of the video, because it is the line that separates a careful viewer from a careless one. Surprising is not the same as inexplicable. A thing can be astonishing and still be understood. In fact, that combination, astonishing and understood, is the best thing science ever produces. The dramatic version of this story asks you to trade the genuine astonishment for a manufactured mystery, to give up the real and satisfying explanation in exchange for a vague and ominous one. That is a bad trade. Do not make it. The true story here is not smaller than the rumour. 4 spacecraft scattered across the inner solar system, relaying a record-breaking signal around our star for 19 days, while scientists invented a new technique to pin down its hiding place. That is not a lesser story than a galactic conspiracy. It is a far greater one, and it has the singular advantage of being true. Part 8. What the Sun was really telling us. So let us stand back, all the way back, and look at the whole shape of what happened. Because when you assemble the pieces, this turns out to be a story with a meaning, and the meaning is not the one the dramatic version was selling. In August of 2025, the Sun produced a radio burst that nobody noticed and nobody cared about, because it looked exactly like the thousands of ordinary bursts that came before it. And then it kept going. It ran for 19 days, against a previous record of about 5, and a typical lifespan measured in minutes and hours. It nearly quadrupled the longest such event ever recorded. It did this not through one violent moment, but through patience, through a magnetic structure in the Sun's atmosphere, a helmet streamer, holding a population of energetic electrons trapped and radiating, while a trio of coronal mass ejections from the same region refueled that trap again and again, reinforcing the cage and topping up the reservoir, keeping the broadcast alive long past the point where it should have faded into silence. And we only know any of that because of what we have built. Because 4 spacecraft, Stereo and Parker Solar Probe and Wind and Solar Orbiter, none of them designed as a team, all of them happening to be operating at once and scattered across the inner solar system, were able to pass the observation between them like runners in a relay as the Sun's rotation carried the source around. Because scientists invented a new technique, grounded in Stereo's particular way of seeing, to pull a precise location out of a blurred and moving signal. Because the painstaking work got done of stitching 4 spacecraft's fragments into one continuous 19-day record. And because that record was written up, checked by other scientists, and published, so that it became not a rumour but a result. Now hold the 2 readings of this event side by side one last time. There is the version that says the Sun is misbehaving, doing something inexplicable, sending a signal nobody can account for, a symptom of some larger and darker change reaching all the way out to the galaxy. And there is the version the actual science supports. That version says the Sun, an active and variable star, produced a rare but explicable event, an extreme alignment of ordinary ingredients, and that a fleet of human-built machines and a community of human scientists caught it, tracked it, explained it, and published it. One of those versions asks you to be afraid of something you do not understand. The other asks you to be amazed by something you can. And I want to make a case, gently but firmly, for why the second version is not just the more accurate one but the better one to carry with you. The fearful version feels, in the moment, like it is taking the event more seriously. It feels weightier, more significant, more urgent. But look at what it actually does. It takes a genuine achievement, a real piece of human understanding hard-won by scientists and spacecraft, and it throws that achievement away in exchange for a vague dread. It trades something solid for something hollow. The grounded version asks more of you. It asks you to follow the physics, to hold the distinction between unprecedented and unexplained, to sit with an honest open question instead of a tidy scary answer. That is more work. But what it gives back is real. It gives you a true thing. It gives you the genuine astonishment of a star that broke a record, and the genuine pride of a species that was watching closely enough to catch it, and a real, open, exciting question about what else is out there to be found. Fear gives you a feeling. Understanding gives you the world. And when those two are on offer, I think it is always worth doing the harder work to take the second one. There is also a quieter point buried in here about how to be a good consumer of stories like this one, and it generalizes far beyond the Sun. When you encounter a piece of news that is genuinely surprising, a record broken, an anomaly reported, an unexpected reading from somewhere in nature, the most useful question you can ask is not, is this scary? The most useful question is, has this been explained, and how do they know? Ask whether a mechanism has been identified. Ask whether it has been through peer review. Ask whether the people presenting it are marking clearly what is settled and what is still open, or whether they are presenting pure certainty and pure alarm. Those questions will, again and again, separate the version of a story worth trusting from the version worth setting aside. This solar burst is, in a way, a perfect training case. It is genuinely dramatic, so the temptation to fear it is real. And it is genuinely explained, so the grounded reading is right there for anyone willing to follow it. If you can practice holding the line on a story like this one, the line between astonishment and dread, you will be better equipped for the next surprising headline and the one after that. And here is the thought I want to leave you with, the one that I think is the real lesson buried inside this 19-day signal. We spent a whole section on the genuine open question of whether the sun has been producing bursts like this all along, in the dark, around its far side for as long as it has been a star, and we simply could not see them until now. And I told you that question is not yet settled, but notice what that question really is, underneath. It is not, at its core, a question about the sun, it is a question about us. It is the recognition that for almost the entire history of our species, the sun could do something extraordinary, and we would never know, because our eyes only reached as far as one window, and the sun would carry its secret around to the far side and we would lose it. That is not true anymore. For the first time, we have built enough eyes and placed them in enough different parts of the solar system that our star can no longer simply turn away from us to hide what it is doing. A burst can last 19 days and rotate clear around the sun, and we can follow it the entire way. We have, in a real and literal sense, surrounded our star with attention, and the 19-day burst is the first clear proof of what that new capability can catch. Think about what that represents in the long view. For almost the entire span of human history, the sun was something we could only look at, never around. We stood on one planet with one vantage point, and we saw the one face of the sun that happened to be turned toward us. The other side, the far side, was a permanent blind spot, a hemisphere of our own star that no human being had ever seen until the space age. And even once we could see the far side, watching the whole sun continuously, with no gaps, as features rotated from one side to the other, required something more than a single distant observatory. It required a distribution of instruments, a spreading out of our attention through the solar system itself. The fleet that caught this burst is the result of decades of patient, expensive, often unglamorous work. Mission after mission, each one adding another vantage point, until almost without anyone declaring it a milestone, we crossed a threshold. We reached the point where the sun cannot fully hide from us anymore. The 19-day burst is in a sense the first big thing we caught on the other side of that threshold. It is a demonstration that the threshold has been crossed, and once you see it that way, the burst stops being a slightly unsettling headline and becomes something closer to a milestone in the relationship between humanity and our star. It is the kind of thing that could only have been caught now, by us with what we have built. A century ago it would have been invisible. 50 years ago it would have been a fragment. Today it is a solved case in a journal, with a located source and an identified cause, and a brand new technique left behind as a tool for the future. The same event occurring at 3 different points in history produces nothing, then a fragment, then a complete and understood scientific result. The sun did not change across those 3 moments. We did. So when people ask whether the sun is changing, I think the more honest and more interesting answer is this. And notice that this is, in the end, a hopeful realization rather than a frightening one. A sun that we can finally watch in full is a sun that can surprise us less and less with things it has hidden, and teach us more and more with things we can now see. Every gap we close in our coverage is a gap the sun can no longer use to keep a secret. We do not yet know if the sun is doing anything new, but we are, without question, doing something new. We are watching our star with a completeness that no generation before us could have imagined, and the inevitable consequence of watching that closely is that we are going to keep finding records we did not know were there to be broken, and behaviours we did not know our star had, and events that sat in the sun's repertoire all along unseen, simply waiting for us to finally be in a position to notice. The sun did something we have never seen before. That much is true, and it is the honest headline, but read it carefully, and notice where the emphasis really belongs. The remarkable thing is not only what the sun did, the remarkable thing is that this time we were finally watching closely enough to see it. And the unsettling, thrilling, wide-open question that follows from that is the one I will leave hanging in the air, because the scientists have left it hanging too. If a 19-day burst was hiding in plain sight until the exact moment we built the means to catch it, then what else is our star doing right now in the spaces we still cannot see? We have surrounded the sun, but we have not yet seen all of it, and the next record is almost certainly already underway. Somewhere on our star right now, a structure may be quietly holding its energy, waiting out its own slow rotation, while we have not yet thought to look. And the only thing we can say for certain is that, this time, when it finally reveals itself, we will be watching.